Welcome to Astronomy Speakers Night at the David Dunlap Observatory, online with the Royal Astronomical Society of Canada, Toronto Centre. My name is Denise Chilton, and I am the RASC Toronto Centre DDO Committee Chair and an operator of the 74-inch telescope here at the David Dunlap Observatory. Together with our outreach coordinator, Quinton Wayrich, I am delighted to be your host for tonight's lecture. I'm very excited to welcome you, our viewers, to tonight's lecture. If you haven't already, please take a moment and say hi in the YouTube chat and tell us where you are joining us from. This helps us to make sure that all of our technology is working properly. The Royal Astronomical Society of Canada's mission is to enhance understanding of and inspire curiosity about the universe through public outreach, education, and support for astronomical research. In partnership with the City of Richmond Hill, RASC hosts outreach activities at the David Dunlap Observatory, or DDO. The observatory is home to Canada's largest optical telescope, which, believe it or not, is right here behind me in the dark. We are hoping to have some live views for you tonight if the clouds clear out in the next 45 minutes or so. So we have the telescope set up for viewing, and fingers crossed we will get some clearer skies because of course telescopes can't see through clouds. So everybody keep your fingers crossed and maybe we'll be lucky tonight. We would like to start by acknowledging that the David Dunlap Observatory in Richmond Hill stands on the traditional territories of the Wendat, the Haudenosaunee, and the Anishinaabe peoples, whose presence here continues to this day. We would also like to acknowledge this land is at the meeting place of two treaties, the lands of the Mississaugas of the Credit and those of the First Nations of the Williams Treaty. We thank them and other Indigenous peoples for sharing this land with us. It's my great pleasure now to introduce our speaker for tonight's lecture, Sunna Withers. Sunna is a first-year MSc student at York University. She's studying high redshift galaxies with the James Webb Space Telescope. This currently involves using simulated JWST observations to predict ways to find high redshift galaxies in data that will be collected during the telescope's first year of observations. Once data has been collected, these predictions will be applied to the JWST observations to find these high redshift galaxies. Tonight, Ms. Withers' lecture is titled High Redshift Galaxies and the Early Universe. This talk discusses what is currently known and unknown about high redshift galaxies and some possible breakthroughs that could be made with the James Webb Space Telescope. If you have questions for our speaker, please post them in the YouTube chat. Sunna will have time to take questions at the end of her talk. So please join me now in welcoming Sunna Withers.
Hi, thank you for the introduction. I'm very pleased to be here talking about high redshift galaxies, which is very much related to my research and something I'm very excited about with the launch of James Webb recently and the data even more recently. So before I get started in the talk, I just want to give a bit of an outline of some of the things I'll be discussing today. So I'll first start out with a bit of an introduction about what it means to be a high redshift galaxy and the environment that these things exist in. Then I'll talk about how we observe high redshift galaxies, then the current understanding of high redshift galaxies, and finally a bit about the James Webb Space Telescope. So starting off defining a term that I'm going to be using quite a bit tonight, which is redshift. Redshift has a very general definition, which just describes how the light from an object is redshifted. So it's stretched out and shifted into redder wavelengths based off of something that's happening to the object. The thing that's relevant that causes redshifting that's relevant for us tonight has to do with how the expansion of space redshifts light coming from distant galaxies. So our universe is expanding, it always has been. And as the universe expands, it causes distant galaxies to be moving away from us at very, very high speeds. And what this does is it stretches out the light that comes from that galaxy, shifting it towards redder wavelengths. The redshift of an object is something that is very, very useful to measure because it tells us a few different quantities related to the galaxy that's very important for us to know. The first of all is distance. Objects with the same redshift are the same distance away from us. And since redshift is a measure of distance, it also means it's a measure of time. Specifically, what the redshift of a galaxy tells us is how long it took the light coming from that galaxy to reach us, which is essentially just a measure of how many years we're seeing into the past. Because we don't see galaxies as they are today. We see galaxies as they were when the light was emitted. And this measurement, how far back we're looking in time, is equivalent to measuring the age of the universe when the light was emitted. So I have a couple numbers just for reference on the screen. Redshift 0 is today, where the universe is 13.8 billion years old. If we were to move to an object at redshift 1, we would be observing the universe as it was when it was 6 billion years old. And if we were to move even further back to a redshift of 6, we would be observing the universe as it was when it was only 1 billion years old. And that's really just the key point to remember here, is that the redshift of an object just tells you the age of the universe that you observe, the time since the Big Bang. And in astronomy, this is an incredibly powerful thing, because when we observe galaxies at different redshifts, you can just observe the universe as it evolves. This is something that astronomers have been doing for a very long time. They've been observing galaxies at higher and higher redshifts, and coupling those observations with observations of the cosmic microwave background, we've been able to put together this picture of what the universe looks like through its evolution, which is just shown here. At the top here, there's 6 different very important epochs to the history of our universe, along with the redshifts that they happen at. And then down here, it shows the age of the universe in billions of years for each one of these epochs. So before I get started talking about high redshift galaxies specifically, we need to do a quick overview of what the early universe looks like, because that's where these objects are going to be existing. And just for reference, here when I say high redshift and the early universe, I'm specifically talking about roughly the first billion years of cosmic history, which is at redshifts 5 to 6 and up. And if I were to say this to some people, they would get a little bit upset, because depending on who you ask, high redshift can mean redshifts 1 to 2 and maybe 3 or 4. But specifically for the purposes of this talk, I mean redshifts 5 to 6 and up, so the first billion years of cosmic history. So let's go all the way back to the very beginning of the universe with the Big Bang. During the Big Bang and right after, all of the material and energy and everything in our universe is just packed into this incredibly tiny area. It makes it very hot and very dense. So particles and energy and matter don't really exist in a state that we're used to dealing with. But like I said, the universe is expanding. It always has been. So over time, as the universe expanded, it became less dense. It allowed matter to cool. And over time, it started to exist in ways that we're used to dealing with. So it started out with fundamental particles being able to form like electrons and quarks. Eventually, those quarks could start to join together to form things like protons and neutrons. And finally, those protons and neutrons could join together to form heavier nuclei, primarily helium with trace amounts of lithium as well. And eventually, when we wait about 380,000 years, corresponding to a redshift of about 10,090, an important event happens, which is called recombination. At this point, the universe is big enough and cool enough because of the expansion that neutral matter can form. So electrons can join together with primarily hydrogen, or not hydrogen, but the protons to make neutral hydrogen. They can also join together with some of the heavier elements like helium and lithium. And during recombination, this emits the cosmic microwave background radiation, which we see a picture of here. Since when electrons and nuclei form neutral atoms, they emit light, which is this cosmic microwave background radiation. And another important consequence of recombination is that the universe has now transitioned from being a dense soup of ionized particles to now being primarily neutral. So this now ushers in the next phase of cosmic evolution, which is called the Dark Ages. So the universe is just now filled with this neutral gas, primarily hydrogen, about 75% hydrogen, 25% helium, and trace amounts of lithium. That's all left over from recombination. There aren't any stars or galaxies or any of the things that we see in the universe today. It's just neutral gas. And it might seem like there's not a lot happening during the dark ages, but something incredibly important is happening here. When the universe began, there were very small density fluctuations that were put in place just due to the formation of the universe. And during the dark ages, these density fluctuations start to grow. During the early dark ages, the density is incredibly uniform in the gas, only having fluctuations of maybe 1 part in 100,000, something incredibly small like that. But because gravity is an attractive force, over time, these density fluctuations start to grow and grow. And eventually, this lays the groundwork for all of the large-scale structure that we see in our universe. So galaxies, galaxy clusters, these amazing filaments in our universe, the groundwork for all of that was laid during the dark ages when those small overdensities were growing. And another important consequence of this is that it eventually allows the very first stars in our universe to form, which starts something called cosmic dawn. So now the neutral gas has been able to clump together enough so that this gas can collapse and form stars. And the stars that are formed during cosmic dawn are called population 3 stars. These are expected to look incredibly different from the stars from later generations of stars like our sun and the generation before it. They're called population 3 stars, and the reason that they're so different than the later generations of stars is simply because of the gas that they formed out of. So these population 3 stars form out of the pristine gas left over from recombination. So this is 75% hydrogen, 25% helium, trace amounts of lithium, and absolutely nothing else. And when these stars eventually die, they live and die incredibly quickly. They're much more massive than later generations of stars like our sun, possibly hundreds to thousands of times more massive. So they die after only a couple million years after their formation. When they do die, they start to chemically enrich the universe. So these stars would form heavier elements in their cores, which astronomers call metals. And it would eject all of those elements, all of those metals out into the gas that surrounds it, which starts to chemically enrich the universe and means the stars that form after population 3 stars look very different because they have these heavier elements, these metals, when they start to form. Eventually, at a redshift of about 12, so still only a few 100 million years after the Big Bang, cosmic dawn eventually gives way to the epoch of reionization. And during the epoch of reionization, galaxies are now starting to form and grow. So at first, during cosmic dawn, we had the first stars, and reionization gives way to the very first galaxies. And the first stars and the first galaxies forming in our universe do something incredibly important, which is that it reionizes the universe. It changes the gas that surrounds these galaxies from being primarily neutral to being primarily ionized. So reionization starts at around cosmic dawn with the first stars. They emit high energy radiation that's capable of ionizing hydrogen, so it's breaking it apart into a proton and an electron. And over time, once you have the first galaxies start to form and more galaxies start to form after that, the universe gets more and more ionized. At first, it kind of looks like Swiss cheese. You have these small pockets of ionized gas that are embedded in this neutral gas. But over time, those pockets grow and you get more of them. And eventually it transitions to small pockets of neutral gas in primarily ionized gas. So we know that that reionization started at around redshifts, maybe 12 to 15 during cosmic dawn, and we're complete by around redshift 6 with a mostly neutral universe. So now I'll move on to talking a bit about how we find high redshift galaxies now that we understand kind of what environment that these galaxies exist in. And there have been quite a few galaxies that have been identified during the epoch of reionization, primarily over redshifts of about 6 to 8, so the later end of reionization. But once you get at redshifts above 8, there are very, very few known high redshift galaxies, maybe only about 10 to 20 known at this highest redshift range, with the most distant galaxy ever being found at a redshift of about 11. And also a very notable discovery that's pretty new here is the discovery of a single star during the epoch of reionization. It's called Earendel, discovered at Redshift 6.2 only a couple months ago, I believe, by the Hubble Space Telescope. So definitely a very, very remarkable discovery on the part of Hubble. The way that these high redshift galaxies are typically found is just by doing two different things. So first of all, astronomers start off by taking direct images of galaxies in several different filters. So they target multiple different wavelengths of light that come from the galaxy. And then they use those direct observations in different wavelengths to get an estimate of what the galaxy's redshift is. This is pretty effective, but it does have several sources of error associated with it. So if you want to truly confirm that you found a high redshift galaxy, you need to use a spectrum. So astronomers, once they have identified possible candidates of high redshift galaxies, they then go and observe them with telescopes to get their spectra to determine their redshift with more precision. The problem with finding high redshift galaxies and single stars at high redshift in some cases is that these galaxies and sometimes stars are so incredibly dim that they're just really hard to see. They can have magnitudes of 29 to 30, sometimes even dimmer than that, or oftentimes even dimmer than that, actually. So you need the deepest images to be able to find them. And those deepest images are provided using deep fields. So these are just images of typically very small regions of the sky that have very long integration times. So you'll point a telescope at a region of sky for days, weeks, sometimes even months to be able to pick up the very, very dimmest objects that exist in that field. And there are several different deep fields that have been done over the years, but probably the most famous come from the Hubble Space Telescope and also some of the most important ones. So the very first deep field ever taken was taken by the Hubble Space Telescope all the way back in 1995. And they're quite common now because of how successful they were. But back in 1995, this was a very odd thing to do. The first Hubble Deep Field North, which is shown here, was originally proposed by the director of the Hubble Space Telescope at the time, Robert Williams, who basically just wanted to see how dim of objects that the Hubble Space Telescope could pick up. So when this telescope is really pushed to its limits, what is the dimmest object that it's going to see? So he proposed doing observing completely backwards. Typically, when you want to observe something, you have a target in mind. So it's a galaxy you want to study, or just something you want to take a picture of. You point the telescope at it, and then you process and use your data however you like. But what Robert Williams proposed doing was just finding a patch of sky with nothing in it. No bright stars, no bright galaxies, and just point the telescope at it for a while and see what it finds. So that's exactly what he and his collaborators did. They ended up finding a patch of sky about 1/12 the size of the full moon, so pretty small, that had really nothing in it. This patch of sky is right above the Big Dipper, and they pointed Hubble at it for 10 days, resulting in the first Hubble Deep Field. You can see a couple objects like here or here that are stars, but apart from that, every point of light in this image is a galaxy. And this is remarkable. At the time, it detected the most distant galaxies ever found and the dimmest ones, so it expanded the redshift frontier to a redshift of 4 about 1.4 billion years after the Big Bang. Those are the highest redshift objects that had ever been detected. And on top of doing that and making these groundbreaking discoveries, it also sort of changed course of astronomy a little bit, because people realized, like, this is a really good idea. And if we want to find really dim and really distant objects, we're just going to keep doing this because it worked out really well. So this Hubble Deep Field North was then followed up with another deep field in the south called the Hubble Deep Field South, because astronomers are not very creative at names. And it had the exact same results. They just basically wanted to confirm that you find the similar results regardless of where you point the telescope, and the Hubble Deep Field South confirmed that. Then moving forward, Hubble went on to do several other deep fields that not only went deeper, so they observed the sky for longer periods of time, but they also expanded the wavelength coverage. The first Hubble Deep Fields North and South were only done using visible light, but then they eventually expanded the wavelength coverage to include the ultraviolet and infrared wavelengths that the Hubble Space Telescope can cover. These infrared wavelength observations are particularly important for high redshift astronomy because the light coming from galaxies at high enough redshift is completely redshifted out of the ultraviolet and visible light. They're really just not emitting anything in ultraviolet and visible that we can see, because their light is redshifted all the way into the infrared. So if we want to be able to observe the highest redshift galaxies, we really need that infrared light. So just a couple examples of other deep fields that Hubble did. There was the Hubble Ultra Deep Field, which observed for a patch of sky for 11 days and reached galaxies at redshift 7. Then there's the Hubble Extreme Deep Field, which is shown on the screen here, which observed a smaller patch of the Ultra Deep Field for 50 days, reaching redshift 11 galaxies. And finally, there was the Hubble Legacy Field, which included total exposure times totaling 250 days, except it expanded the area of sky that it covered. So it covered a much wider region than the Hubble Ultra or Extreme Deep Fields. It didn't go as deep as the Hubble Ultra or Extreme Deep Fields, but it did encompass a wider area of sky, which can be very useful for a lot of things. So following the success of the Hubble Space Telescope doing these deep fields, a lot of other observatories jumped on the bandwagon and started doing their own. And oftentimes they observe the same fields. So these extreme and ultra deep fields that were observed by Hubble have been observed by multiple other observatories. And it might seem a little bit counterintuitive to have all the observatories observing the same field, but it's actually a very useful thing because it tells you a lot of different information. Different light tells you different things about a galaxy. So for example, ultraviolet and visible light will tell you about the young stellar populations, the stars that have just formed. But if you observe the same thing using infrared light, you can learn about some of the older stars that are in the galaxy. And one of the examples of these, deep fields that have been observed by multiple different observatories is this Great Observatories Origin Deep Survey, or GOODS. There are two fields about 16 by 10 ArcNet wide, one in the north and one in the south. This is an example of one of the GOODS fields outlined in yellow. You can see that it covers the Hubble Extreme and Ultra Deep fields. And then this wider area here encompasses the Hubble Legacy field that I mentioned before, with the 250-day long integration times. And this Great Observatories Origin Deep Survey gets its name from NASA's 4 great observatories which study these fields. So it includes wavelength coverage from the Hubble Space Telescope, from the Spitzer Infrared Telescope, the Chandra X-ray Observatory, and the Compton Gamma Ray Observatory as well. It ended up being that this field wasn't only observed by space telescopes, but it also includes some collaboration with ground-based telescopes as well, like the Very Large Array radio telescopes. And these GOODS fields are probably some of the most revolutionary observations in astrophysics, especially for high redshift astronomy. They found hundreds of galaxies during the epoch of reionization, including most of the galaxies that we know at redshifts greater than 8 and 9. And it also includes the most distant galaxy ever discovered, GN-Z11, shown right here, which is at a redshift of about 11.1. Then the data from the GOODS survey is continuing to be analyzed today, and it's continuing to be updated with new observations from observatories. And eventually this will include observations from the James Webb Space Telescope. So this field has such a wealth of information that has done so many things for astronomy, and will continue to do a lot of work in the future as well. So I'll now start talking a little bit about the properties of high redshift galaxies, now that you know I've talked about how we observe them. And there's still a lot that we don't know about them, but we do have a general idea of what these galaxies look like. So just a quick summary of their properties. These galaxies are generally very small and compact. They're less than about 1 kiloparsec in size, and for reference, the Milky Way is about 30 kiloparsecs in size, so these things are tiny. They're also low mass, which makes them dim. It's very uncommon to find a high mass and bright galaxy during the epoch of reionization, because they really just haven't had time to form and accrete that much mass. Galaxies also have very irregular morphologies. When I say irregular morphologies, I don't mean like irregular, disturbed from collisions or interactions with other galaxies. They really just don't have any structure like the spiral arms in the Milky Way, because they really just haven't had time to form that. So here's just some examples of what these high redshift galaxies look like using observations from the Hubble Ultra Deep Field. You can see that all of these do look pretty small and compact, and they don't have a lot of structure. Some of them just sort of look like compact balls, whereas other ones do have a bit of weird stuff going on around them, which is probably just evidence of how they're forming. So in addition to the way that they look, these galaxies also tend to have very high star formation rates. So they're forming stars at rates of even up to sometimes 1,000 solar masses a year. And the reason for this high star formation rate is simply because they're surrounded by a ton of cold neutral hydrogen. And these galaxies over time will start to accrete this cold neutral hydrogen, and that really feeds the star formation in the galaxies. So they can form stars at very, very high rates. Because they have high star formation rates, they're dominated by young stellar populations. They also really haven't had time to form any older stellar populations. So the entire galaxy is just dominated by these young, newly formed stars. This also means that the galaxies are very metal poor, so they don't have a lot of heavier elements like carbon or oxygen. And it also means that they generally don't have very much dust. And all of these properties end up being reflected in the spectral properties of the galaxies, which is ultimately that they look very blue and they have very strong emission lines. And before I move on here, I just do want to point out one thing, which is that I just told you that high redshift galaxies are blue, but all of these high redshift galaxies here look very red. And the reason for that is simply because the light coming from the galaxies, while it was emitted and very blue when it was emitted, these are all redshifted far into the red and infrared wavelengths. So they all look very red here simply because we're just observing them as they are redshifted and not as they are in the rest frame looking very blue. If we were to account for the redshifting effect, they would all look very blue here instead of red. So given that high redshift galaxies have properties that are very different from lower redshift galaxies, and they exist in a time that looks just very, very different to what we see at lower redshift, there are a couple new kinds of high redshift galaxies. And I'm going to talk about two of the most abundant ones at high redshift. So the first one are these Lyman break galaxies. And these are just characterized by a very strong decrease in their brightness at wavelengths below 912 angstroms in the rest frame. Now, this measurement of 912 angstroms is very important because photons, particles of light, which have wavelengths of 912 angstroms and below, are energetic enough to be able to ionize hydrogen. And since galaxies at high redshift are embedded and surrounded by a ton of neutral hydrogen, what happens is that when high redshift galaxies emit photons capable of ionizing hydrogen, they inevitably run into a hydrogen atom not long after they're emitted, and they knock the electron off of the atom, ionizing the hydrogen. This overall does help to reionize the universe, but also means that we just can't see the light that comes from galaxies at wavelengths below 912 angstroms. And Lyman break galaxies are a pretty useful thing to find because they produce a great signature in the data, which is shown here. So here we have observations of a high redshift galaxy using infrared light, green light, blue light, and ultraviolet light. And what you can see here is that in these redder wavelengths, in the infrared, green, and blue light, you're getting a signal from the galaxy. You can see it pretty clearly in the image. But once you head off to the ultraviolet light, we don't see the galaxy at all. And this is just because the wavelengths that this ultraviolet light are probing have wavelengths shorter than 912 angstroms. So the galaxy just doesn't exist here, and we can't see it because all of the light that should be coming into this filter is just being absorbed by the neutral hydrogen around the galaxy. So this makes them a pretty easy and convenient thing to look for because this is a very clear signature in the data and is also somewhat hard to replicate with other objects. So when astronomers go looking for high redshift galaxies, they typically do look for these Lyman break galaxies and this easy signature to pick out. And then the second kind of galaxy that's very abundant at high redshift are these extreme emission line galaxies. These galaxies have incredibly strong emission lines in visible and UV light. So these are things like the oxygen 3 emission line, hydrogen alpha, and hydrogen beta emission lines. Some of these you see in star-forming regions like the Orion Nebula. If you look at Orion, it can look a little bit green, and that's because of emission lines like the O3 emission line. So star-forming regions have very strong emission lines like this. And the reason for this, especially in these very most extreme emission line galaxies, the thing that produces this is the fact that these young stars in a galaxy produce a very hard and strong radiation field, which is capable of creating emission lines like this. And at lower redshift, we do observe some extreme emission line galaxies. Green peas and purple grapes from the Sloan Digital Sky Survey are examples of low redshift extreme emission line galaxies. But they really aren't that common at lower redshift because the conditions to make extreme emission line galaxies aren't common here. But they are at high redshift. Most high redshift galaxies have young stellar populations and don't have much gas, don't have much dust. So most of the galaxies at high redshift produce the conditions to see extreme emission line galaxies. So at this point, current estimates say that over 50% possibly of the galaxy population at high redshift could be these extreme emission line galaxies. So they're very, very common at high redshift, and these can tell us a lot about galaxies at high redshift and are, again, very useful to observe. So that's kind of the overview of everything that we know, or we think we know at least, about high redshift galaxies and the early universe and the way that relates to those high redshift galaxies. But the thing is that there's still a lot to be learned about them. We just kind of at the moment lack current the instruments that we need to fully probe and fully investigate this era of the universe. So there's still a ton of things that we don't know. And just a couple quick points of things that we don't know. So first of all, there's a lot of questions surrounding the formation and the evolution of the very first galaxies. We know that the galaxy buildup has to be underway by redshift 8 because we found fairly large galaxies at redshift 8. We also know that star formation and galaxy buildup has to have started at around redshift 15, simply because we observe galaxies like GNZ11 at a redshift of 11, which has to have had time to build up to its current state. But apart from that, we don't really know too much about the physics of galaxy formation and how the first galaxies formed and evolved. So we want to learn about how these galaxies are forming stars. We want to learn about the physics of star formation. And it might seem a little bit ridiculous to try and learn about the physics of star formation here, because the physics of star formation you would think would stay constant with time. But the reality is we just don't know that. Population 3 stars we expect to look so different from lower redshift, from later generations of stars. So it's possible that the physics of star formation at this earlier time could be completely different from what we see today. There's also a lot of questions concerning the epoch of reionization and the history of that. We know that it started at around redshifts of 12 to 15 with cosmic dawn and ended by a redshift of about 6. But we really don't know all that much about what happened in between. So, for example, was reionization fast? Did it complete mostly early on and then just kind of slowly trickled to finishing reionization closer to redshift 6? Or was it slow and it sort of dragged slowly during the earlier days and then completed very fast closer to redshift 6? We also sort of believe that the driver of reionization, so the objects that were most responsible for reionizing the universe, has to be small galaxies in the early universe. But the reason we know this isn't because we've observed these galaxies, it's just because they're really the only option. We know that there weren't a lot of active black holes in the early universe, so they couldn't have done it. We don't find a lot of massive galaxies in the early universe, so those have to be ruled out. So the only option is that there's a whole population of dim galaxies that we just can't observe, and that has to be what's responsible for reionization. But again, we haven't found these. So we want to be able to find these galaxies and characterize them and confirm what we think. In practice, the way that all of these things are going to be accomplished is just by observing more high redshift galaxies. This is particularly true at the highest redshift end, so redshifts greater than 8, because there are so few known galaxies there. There's really not enough known galaxies in that era to get a good idea of what they look like and to be able to fully characterize them. So we really need to expand the sample of galaxies in that era. We also need to be able to expand the redshift frontier beyond redshift 11, where it is now. So we want to be able to observe the very, very first galaxies in our universe. So closer to redshift 14 and 15. We want to be able to observe galaxies there and then characterize them as well. And then finally, another big question is, what do population 3 stars really look like? We've never observed a population 3 star. Everything that we know about population 3 stars comes from our knowledge of how stars work and from plasma physics. And it is a relatively straightforward thing to do, but it still doesn't change the fact that we don't have any observational confirmation for what we think is true about these stars. So we need to be able to observe them and characterize them, figure out how big they got, how many of them formed. Is it possible that some very, very low mass population 3 stars were able to form and they still exist today? So these are all things that we really just don't know and we need to be able to answer. And to do that, we need to have a set of next generation observatories. The field has been a little bit stalled because we just haven't had these new observatories coming online, but there are several of them that will be coming online within the next decade. I would love to talk about all of them, but we don't really have time for all of that. And I think the most exciting one, at least for now, is the James Webb Space Telescope, which just came online this week. So a quick just summary of JWST and what it is it's a 6.5 meter infrared telescope. There's a picture of the primary mirror here, which is 6.5 meters and a human for scale. And it covers wavelengths of 1 to 28 microns, which corresponds to the near and mid infrared. Webb specifically is going to be completely revolutionary for high redshift astronomy for 2 reasons. First of all is the mirror size. Its mirror is several times larger than the Hubble Space Telescope, so it's going to be able to detect objects that are so faint, things that Hubble, no matter how much it tries to detect them, really just won't be able to pick it up. And second is its wavelength coverage. So Hubble has a little bit of coverage in the infrared, but not much, whereas Webb is primarily an infrared telescope. And that is a very, very important thing because I think, like I said before, the light coming from the most distant high redshift galaxies is completely redshifted into the infrared. We can't see them using visible light, and sometimes we can't even see them using near infrared light. We have to use mid infrared light. So no matter how hard Hubble tries, it will never be able to find the most distant galaxies because it just doesn't have the right wavelength coverage for that. And Webb is going to provide that. So Webb launched on December 25th, 2021. It was literally a Christmas present for people in the astronomical community. And after 6 months of deployments and commissioning and stress, hoping that this thing is going to work, we finally find out that it did work, and it's been working. It's absolutely amazing. It started science operations officially on July 12th with the release of 5 fantastic images from the telescope. And it is now starting to do the thing that we've been waiting for it to do for years, which is to really investigate high redshift galaxies among its other science goals, of course. So the first year of observations with Webb is currently planned. And while I can't get into everything that Webb is going to do and all the observing programs that it's going to, all the things it's going to observe, I can give a brief overview of some of the things that we think that the telescope is going to be able to accomplish. And so far with the data we've been getting, looks like this is pretty realistic. So first of all, it's going to be able to complete a full census of the galaxies during the epoch of reionization. This includes galaxies at redshifts of about 6 to 7, but more importantly, it includes galaxies on the higher redshift end, so over redshift 8 to 10. It's not only going to be able to observe these galaxies using imaging, but it's also going to be able to take spectrums of the galaxies, which in a lot of cases can be a lot more valuable than simply the direct images of the galaxies. So this is going to completely revolutionize the view of galaxies during the epoch of reionization. It's also going to be able to find galaxies up to a redshift of 15 and possibly beyond. So these are the very, very first galaxies that are forming in our universe that Webb is going to be able to see. It's also going to be able to map the structure of the early universe, which will just help us learn more about how reionization proceeded. So was it fast or was it slow? And a couple of the things that it's going to observe is doing follow-up observations of deep fields like the Goods fields and doing some deep fields of its own. And it's also, interestingly, going to be observing Earendel, that single star at redshift of 6.2, which can actually teach us about reionization just by observing that single star. And the last thing that I want to talk about here is some of the observing programs that are going to lead to some of the first science in high redshift astronomy. There's a ton of observing programs that it's going to be doing during its first year. They're all going to be incredibly valuable, but there are 3 of them where the data is already being released to the community. So these will be the first observations that will produce real science from the observatory and are definitely worth looking at in a little bit more detail. So there's a few of them labeled here, and I'll talk about them in the next couple slides, but I do just want to give a bit of a heads up, is I pulled some data off of the archive from James Webb today and processed some of those pictures quickly so I could put them in this talk. So there's 4 images, 2 on the next 2 slides that I'm going to show, that are real data, real color images from the James Webb Space Telescope. But just a heads up, they're not going to look as good as some of these other James Webb pictures you've seen, just because I kind of did it quickly and didn't pay as much attention to detail as some of these other programs. So these are Webb images, but they are not the best ones you will ever see, but here they are anyways. So the first program I want to highlight a little bit is called Through the Looking Glass. It does a spectroscopy of this field called Abell 2744. It's a massive galaxy cluster. So it'll be doing spectroscopy of a lot of objects in this field, identifying a bunch of high redshift galaxies that are in the background of the field itself. You can see a couple tiny points of light around here, primarily around the edges. And those are all, a lot of them are distant high redshift galaxies that Webb is going to be able to pick up and do spectroscopy of. And on top of that, it also includes imaging of some other nearby fields using this. This is taken using the near infrared camera. This is not of the same Abell 2744 field, but it's just of a field nearby. And by using this imaging from the near infrared camera, it's going to be able to identify a lot of galaxies in that era. So the main point of what this program is it wants to take extensive observations of galaxies all the way from the epoch of reionization to a redshift of about 1, where the universe was about 6 billion years old. So this program will do a lot to investigate not only high redshift galaxies, but also galaxy evolution through time, and will definitely produce a lot of amazing results early on in Webb's history. The second is this Cosmic Evolution Early Release Science Survey, which includes imaging in the near and mid-infrared of some deep fields, some of the Hubble deep fields. So the Candles field is an example, which is part of GOODS. It will observe some of the Hubble deep fields using, again, mid and near infrared light. These are 2 examples of the observations using the near infrared camera. And it's going to pick up, again, lots of tiny dots in this image. A lot of those are high redshift galaxies. And this Cosmic Evolution Early Release Science Survey is specifically designed to target the high redshift galaxies. So it's going to be doing a lot of imaging of high redshift galaxies during the epoch of reionization, finding a lot of new ones. It'll also be able to do spectroscopy of these objects because it does include near and mid-infrared spectroscopy as well. And finally, this will push the redshift frontier out to a redshift of 13, possibly even higher. So this program specifically will detect the highest redshift galaxies that we have ever discovered in the universe. And finally, last but not least, is this gorgeous image that we have all seen, part of SMAC 0723, which was released on Monday, and then more detail about it was released on Tuesday. And so far, out of all of the programs and all of the things I've read about Webb, all the amazing things that it's done, it's this image and these spectra right here that are the most, that really pop out the most to me. And let me explain why that is. This image right here only took Webb 12.5 hours to do. And in it, it's identified 2 of the most distant galaxies that have ever been identified. So these are redshift 8 and 9 galaxies that Hubble had so much trouble finding. Webb did in 12.5 hours. And not only that, it went and it got spectrums of these galaxies. And this is something that the Hubble Space Telescope will never be able to do. No matter how hard it tries, it will not be able to identify high redshift galaxies this quickly and this easily as Webb did. In the very first Webb observations that were released, it is already on its way to surpassing what the Hubble Space Telescope has done. So this is really an amazing outlook for what this observatory is going to do. It has an expected 20-year lifespan. And if it can do this in the first data release, I can't wait to find out what this is going to do. It's going to be completely revolutionary for high redshift astronomy. It will answer questions that we didn't know to ask. So this is definitely a very, very exciting time to be in high redshift astronomy with this fantastic telescope. Will completely revolutionize our view of the universe. So that's really all I have for you today on high redshift galaxies. But just as a heads up, if anybody loves Webb as much as I do, you'll want to probably know where you can find more information. There's a couple general information links from NASA's websites right here. If you want to learn more about some of the science that Webb is going to be doing, not only relating to high redshift astronomy, but just in general, you can read through a list of the approved programs on the Space Telescope Science Institute's website. Webb also releases these weekly observing schedules, so you can check to see what the telescope is observing at any given moment, also on Space Telescope Science Institute. I checked before this talk, and for anybody that's interested, Webb has been doing spectroscopy of a quasar for the past couple hours and will be for the next couple hours as well. And then finally, if anyone is interested in processing their own data from the Webb telescope, this is all available online. Some of it does have exclusive access periods where only the people that applied for the observations can get them. But those do eventually expire, and there is still a ton of stuff available online. This is all accessible via the Mikulski Archive for Space Telescopes, or the MAST portal. So you can find it at this link, or you can just Google MAST portal Space Telescope, and the link will pop up. You can search through all of the Webb data and pick what images you want to release. So thank you so much for listening to me talk about high redshift astronomy. It's a lot of fun, something that I really love, and I hope you enjoyed it. Thank you.
Wow, Sunna, thank you so much for sharing this amazing look at the research that will be coming out of the James Webb Space Telescope so soon, and particularly with this focus on high redshift galaxies. This has really been fascinating. We are going to check in now with our RASC DDO outreach coordinator, Quentin Wayrich, who has been monitoring the YouTube chat for questions from the audience. Quentin, over to you.
Thanks so much, Denise. And thank you, Sunna, for coming on and giving this excellent talk tonight. I have a few
invitation.
So first of all, ZapFam would like to say that they like your necklace.
Thank you.
So that is the mirror of the JWST.
Yeah,
correct?
it's the mirror of the JWST, and there are actually several people on the Webb team who I've seen on the live stream that have these necklaces. It's where I got the idea for it. But yeah, this is the mirror of the Webb telescope.
Oh, that's
it even reflects light too.
Oh, that's awesome.
There's an actual mirror on there. It doesn't focus it like Webb does, but it's still pretty funny walking around and then seeing the reflection of the gold hexagons showing up.
That's great. So we did also have a couple questions about the, I guess, the specs of the telescope.
Okay.
So it was, what redshift does JWST hope to see? Around 20, and it seems that the answer to that question was around 13 to 15. Is that correct?
Approximately. But that being said, the Hubble Space Telescope, they had no idea when it launched how far away we'll be able to see. So I'm really hoping that it'll even see even further than that. There's a chance that it could detect population 3 stars. This is still a bit of a toss-up because it depends on other factors. The stars themselves, we think, are just too dim to be observed on their own. But if you look here, you can see these sort of arcs here. This is gravitational lensing. So this is a massive galaxy cluster, a very heavy galaxy. And when there's something directly behind it and its light is traveling towards it, the gravity of that object can distort the light and turn it and have it sort of turn around the galaxy. So instead of seeing this source as a point source, as a galaxy, we see it as this extended arc. And this is great for magnifying the light. It essentially just makes a really big magnifying glass. This is the way that individual star at redshift 6.2 was found by Hubble. So there is always a chance that we could find a population 3 star with the Webb telescope if it gets lensed like this by a cluster. So this is a hope. I really hope they find one, but it's not a guarantee.
So remind me again what redshift range population 3 stars are in?
Closer to 20 to 30.
Wow. Okay, that is exciting.
Yeah.
So another question is, what Z was that 13.1 billion year old galaxy JWST just got a spectrum from? And looking at the slide, I think it was somewhere between 3 to 9.
Yeah, so they highlighted here just some of the most distant galaxies that they did find. Covers a range of redshifts. They found one at 3, one at 6, one at 8, and one at 9. And these were the ones that they told us about. they actually did spectroscopy of, dedicated spectroscopy of 48 objects in this field. So it's possible that there are also a few more Redshift 8 to 9 galaxies in this field that they just didn't put in the figure and haven't told us about yet.
Oh, that is so exciting.
I know.
Okay. I also wanted to ask, why exactly are they called population 3 stars?
Okay, this is a bit of a weird naming convention. So the first generation of stars is called population 3, the second generation is called population 2, and the third generation is called population 1. So it's completely reversed. Our sun is a population 1 star, so it's the third generation of stars in the universe. And I think the reason for this is just because astronomers discovered population 1 stars first, population 2 stars second, and then inferred that population 3 stars have to exist. It was something ridiculous like that. There's no real deep reason behind the naming. It was just sort of how it ended up.
There seem to be a lot of artifact names like that in astronomy, I've noticed.
Yep.
We have another question from the chat here from Eric Briggs. Are the redder galaxies that are being gravitationally lensed being magnified so they appear a lot larger on the image than they are for real?
Yeah, they're being magnified. So one of the interesting things here, and there was a paper, the first paper from JWST was actually published today, which deals with looking at these lensed arcs. And one of the things that they figured out is that not only is this galaxy magnified and stretched out so it looks really weird, but it's actually being magnified twice. So this and this are the same galaxy. This happens a lot with lensing when you have specific sets of circumstances, is that you can get things that are called Einstein crosses. So you have the same galaxy that's lensed and multiplied 4 times. You see it 4 times in the same image around the lens. So lensing does a lot of weird stuff. It magnifies light, it stretches it out, makes it look weird. This is another example of it right here. You can see this galaxy in the foreground right here is lensing a galaxy behind it and really stretching it out and making it weird.
That is so interesting.
Mm-hmm. If you have the time, I highly recommend downloading a full resolution of this off of NASA's website and just zooming in and scrolling through it. It's really cool.
All right,
find
I know
a lot
what I'm
of
going to do for the
interesting
next
things.
3 hours. Thank you.
Yeah. I did that for a few hours when the image was released. It was the first thing I did. Just downloaded it and like zoomed in and looked for cool stuff. So it was a lot of fun.
I have another question. Why is it that Webb needed to be a space telescope?
That's a very good question. The short answer is the atmosphere is really annoying. It is great for supporting life. It is not great for astronomy. So one of the issues with the atmosphere is that it blocks out certain kinds of light. So observing in the infrared through the atmosphere is pretty challenging. It not only blocks out infrared light, but it also emits a lot of infrared light as well, which just makes it challenging to see through it. And another thing has to do with atmospheric turbulence. So when you look at the sky and you see stars that are twinkling in the sky, that's because the air in the atmosphere is moving around and screwing up the light that we see from the star. And unfortunately, telescopes are susceptible to the exact same issues. So you can have a really huge telescope, but if you point it through the atmosphere, it won't produce the resolution and the precision that you want it to, or that it could when the atmosphere isn't there. And there are some ways around this, adaptive optic systems, for example. If you've ever seen pictures of telescopes shooting lasers into space, that's an adaptive optic system where they can measure the distortion of the atmosphere in real time and have the mirrors deform to counteract that distortion from the atmosphere. But there is always a limit to how much this can be done. So ideally what you do with telescopes is you just put them in space. You get around all of the problems related to the atmosphere, and it can just function a lot better in space. Of course, it does create its own set of problems, but for certain telescopes like Webb, it's absolutely worth it to be able to do that.
Okay, that makes a lot of sense. I do have another question. Do you know how old the Milky Way is? Because I'm curious if it's been around for a similar amount of time as the high redshift galaxies, or if these galaxies are actually like all older, like if they're from a previous generation of galaxies.
The Milky Way is very old. It did start to form very early in the days of the universe, or very early in the history of the universe, I should say. I can't give you an exact age, but I think it would be likely that some galaxies that we observe, maybe like this, are the progenitors of the Milky Way. So the Milky Way would have started out looking like galaxies like this and eventually evolved into what it is now. So it's likely that some of these very high redshift galaxies, the first ones that we see, would later on go to form galaxies that kind of did look like the Milky Way.
Okay, thank you. That concludes all of the questions, I believe, for tonight, unless anybody in the chat has anything else they want to ask. Okay, I'm gonna call it there. Thank you very much, Sunna.
Okay, thank you.
Thank you so much, Quentin, for relaying all of those awesome questions from our audience. And thank you, Sunna, for answering them in excellent detail. It is such a treat to have you on at this moment, just as we are starting to see some of this amazing data from the James Webb Space Telescope.